They don't sit down. It's 3:59 they used to.
So today we're pleased to welcome Daniela Calzetti to give the CFA colloquium. Daniela got her PhD at the University of Rome in 1992 and then moved to the Space Telescope Institute, where she was briefly a postdoc and then became a member of the research staff there. I think it was about 10 years later that she moved to the University of Massachusetts in Amherst as a faculty member. And she's been there and just recently got, I'm not sure if it's either promoted or demoted, to become department chair of the Department of Astronomy.
Demoted.
Yeah, so it was about 4 months ago, I guess, and she's just getting used to it. So Daniela is very well known for her pioneering work in a broad range of areas related to external galaxies. So her research covers an impressive range of topics related to star formation, how star formation in galaxies is related to gas and the global properties of galaxies, how dust can affect the UV and optical spectra of galaxies, how dust reprocesses radiation to produce infrared emission that can be used as a diagnostic of star formation, and then trying to understand the basic physical principles behind what regulates star formation in galaxies, principally the effects related to feedback that we now believe are very important for regulating star formation, especially in low-mass star-forming galaxies. Daniela's work has had a really broad impact in the field of extragalactic astronomy. In particular, she's well known for the so-called Calzetti law, which is a way of understanding dust reddening in star-forming galaxies. And her seminal work on that paper has been cited close to 3,000 times now already. And so today she's going to tell us all we want to know about star formation in galaxies and its relationship to the processes that regulate star formation.
Lars, thank you very much for ruining my reputation. Okay, I hope you drank enough coffee because this is going to be a veritable tour de force. LEGUS is an HST, Cycle 21 HST Legacy Treasury program. And like all teams that write large projects, we spend 2 weeks writing the science justification and 3 weeks fighting over the acronym. So what I'm going to concentrate is just a tiny fraction of the results that have come out of LEGUS. And please understand that this is not all the results that can come out of LEGUS. First of all, I can't cover everything. And second, we're still working on a number of the papers. So what you are going to hear is just a tiny fraction. Yet I couldn't concentrate it in less than 28 slides. So, oops, what happened? Oh. Oh. Ew. I hope it doesn't. Okay. So, if you could read this slide, there is a list of the 55. Somehow, everyone got erased. It's surprising. Okay, doesn't matter. There are 55 team members. Actually, if you go to our LEGUS web pages, you find the gory details of all the list. But you don't need to know, okay? I'm the PI. That's all you need to know. Why is that important to understand star formation in galaxies? Well, I guess I don't have to convince this crowd that star formation rates are one of the fundamental parameters you can measure in galaxies, together with stellar mass and their gas mass. And how they evolve across cosmic times are telling us something on the evolution of the universe itself. So this is the classical representation of the cosmic star formation rate density per co-moving volume as a function of time, and the beginning, a very high redshift, is called the cosmic dawn. The peak is called the cosmic noon, at least so I've read on papers. No one has defined the local times. I don't want to call it dusk because it sounds too much ominous, so let's call tea time. But what you clearly see is the rise of the star formation rate, average across all population of galaxies as a function look back time, and about 10 million years ago, 10 giga years ago peaked and then went down towards the beginning of the universe. In contrast, the mass assembly of galaxies has clearly raised. You continue to accumulate mass. Stars don't disappear. Star formation, stars may appear or disappear, so star formation rates can go up and down, but the mass continues to grow because stars at the low end of the stellar initial mass function continue to live for over a Hubble time. These parameters, which look well defined in these plots, are blunt instruments because in addition to understand to measure star formation rates masses as one number, you want to understand how they evolve within galaxies and how they evolve with time within the individual population of galaxies. So measuring star formation rates is a little bit of a hocus pocus art. So if you can resolve individual stars, like you can do in local molecular clouds, you simply count the stars or the young stellar objects, and making some assumptions on their lifetimes, you can actually derive pretty accurate star formation rates. So the very, very local half kiloparsec can be pretty much understood in terms of counting the stars. But as you go to larger distances, things becomes less clear, right? You don't resolve individual stars. You definitely don't resolve individual YSOs, at least for now. And you have to interpret the light from galaxies in terms of how many young stars are being formed. The star formation rate involves using a luminosity that traces emission from young stars. And you would think, okay, how hard can that be? Well, the UV, for instance, this is a Spitzer image. I don't have a purely UV image, but UV, the far UV should trace young stars. However, in a galaxy that has been evolving for 12 gigayears or 10 gigayears, the UV can also be emitted by lower levels of star formation up to post-AGB stars and other type of stars that do not have anything to do with the current star formation. So you try to remove all the contaminants and interpret it as a number. In addition, you can see that the star formation definitely is not distributed uniformly across the galaxy. And therefore, you want to understand why certain regions form stars while others are less active. So in addition to the blunt one number per galaxy, you want to understand the physics of star formation itself and therefore help inform models of galaxy evolution. So at least it's no longer a recipe. You can try to understand, if you understand the physics, you can understand how to insert it in models. So this is a collage of actually five if you count the dwarf, of the LEGUS images. But the questions that you want to ask are, when you convert gas into stars, how is it driven? What are the physical mechanisms that dominate when you are collapsing clouds into stars? Why is star formation inefficient? While every dynamical time scale, however you want to measure your star formation, typically it's only a few percent of the gas that collapses, that is or at least the gas that you can measure that is converted into stars. And of course that means that there is a process that impacts the ability of the gas to collapse and keeps it turbulent, okay? How do you inject turbulence in the interstellar medium of a galaxy? Well, the easiest way is to feedback from stars. Okay, so feedback helps maintaining the interstellar medium turbulent, preventing it from collapsing rapidly. Of course, there is also AGN feedback, but we will not touch it because I want to talk about feedback across the entire disk of a galaxy. Feedback can definitely help you with the issue of maintaining the efficiency low, but then it depends on many parameters, like the age of the stellar populations. It's easily understood that no population is not going to provide a lot of supernovae, so you're not going to have a lot of feedback. The distribution of the stellar mass at birth, so if you only have low mass stars forming, you're not going to have a lot of feedback. Okay, you need massive stars. The clustering and location of the massive young stars. If you have a lot of stars in the same location, you can expect that the effects of feedback, the injection of energy and material into the surrounding medium from a cluster of young stars is going to be significantly more impactful on the galaxy than a few stars isolated and distributed across the body of the galaxy. So in practice, what you want to understand is how the star formation is distributed in galaxies, how is this going to affect the evolution of the galaxy itself. We definitely know, and we knew it even before LEGUS, that stars are not randomly distributed in galaxies. It's not a popcorn popping effect. Okay? Even in the presence of spiral arms, it's not a popcorn popping effect. They are hierarchically distributed. And in particular, I want to quote from a paper by Elmegren in 2010, stars form in large regions that apparently fragment in giant molecular clouds and cloud cores in a sequence of decreasing size and increasing density. Young stars follow the hierarchy and so on and so forth. Star clusters occupy the highest density tip of this sequence and trace star formation. This is my addition. Sorry. Apparently, today I have more problems than I wish I had for the computer. Let's see if I can get that out. Okay. I'll click on it, yes. Okay, I'll continue to speak, to talk while this continues to bother me. Where is it?
It's on the other screen.
Great.
Yeah, let's not talk about technology, okay? Okay, back where we were. So there are two types of information here, which are very important to separate. One, stars are not new stars are not randomly distributed. They follow a hierarchy, and they are hierarchically distributed. Two, star clusters follow the hierarchy. Actually, they trace the star formation by forming at the densest tips of the hierarchy. The two are two separate pieces of information, both very useful. And here I show, this is a plot, a simplistic representation that Bruce put in his paper. And these are two attempts at recognizing, identifying those hierarchies within two nearby galaxies. One is M33, and the other is a farther away galaxy, around 60 megaparsecs. But this paper by Adam and Bastian summarizes the concept that the star cluster occupy the highest density tip of the sequence by correlating the brightest star cluster in a galaxy with the star formation rate. So the two are fairly well correlated, and the intercept of the correlation suggests that on average about 8% of star formation is in bound clusters. So the two follow each other, and this is good. Why? Because star clusters, among all star formation, are the easiest first to identify, and we'll see it later in the talk. And second, you can actually give them physical properties, attribute to them physical properties. You can make reasonably well the assumption that they're a single-age population, and then use models like this one, SED-fitting models, to give them ages, masses, and of course remove the extinction. Okay? So you can get ages and masses of these systems, these lumps of new star formation, and do something with that, especially the age. The age is really important. Of course, you're making an assumption that they are single burst population, and are also subject to evolution. They disperse, they move away from their native environment. So it's not a perfect tool, but it's certainly much better than dealing with large-scale populations of individual stars. So amid all of this information came LEGUS. Briefly, is a cycle 21 HST Treasury with 154 primary orbits, 50 star-forming galaxies, but because they're all nearby, we're closer than about 16 megaparsecs, we could not, in many cases, map them all. So we tried to map. For instance, whenever we had a large galaxy, we tried to do a gratocentric radius of some kind. In some cases, the entire galaxy came along in one go. We released the images in 2015, and in May of last year, we released all the stellar catalogs and all the cluster star catalog that we were able to produce. So a total of 50 galaxies, 63 pointings, okay? Just to remind briefly this, remember this number briefly. This is how we selected the galaxies. These are two of the parameter spaces that we used: total star formation rate, specific star formation rate, mass, and morphological type. Although morphological type and mass, they're correlated. Well, most of these parameters are correlated with each other, as you can tell. So we looked at what existed already in the archive, the magenta and cyan points, and we filled in what was missing in both parameters. So we tried to look at more massive galaxies than what had been done by Amherst, for instance, and to distribute the star formation rate density towards a broader range of parameters relative to what had been done, for instance, by the early release observations of the WC3 that concentrated mostly on high star forming systems. 63 stellar catalogs, one per pointing, 34 star cluster catalogs. Once I tell you how we did the star cluster catalogs, it will be understandable why we didn't do them all. Mostly because most people refused after a while. So, 63 star cluster catalogs, you can do a lot with them. But one thing that you can do, because you're resolving individual stars, in galaxies that are pretty nearby, you can do color magnitude diagrams and reconstruct their star formation histories. Now, our images are not very deep, so we are not going back the entire Hubble time. But we have the UV. So we can actually, through the UV, get very fine details, especially in recent times, of what the star formation history looks like, with a lot of wiggles and bumps and hoops. And that's because we are able to identify, for instance, the helium burning stars, the main sequence stars, and all these other characteristics that are far more easily identifiable when you have a U or UV band. Now, as all color magnitude diagrams, your problem is always the presence of dust. So we decided to start from the easiest cases, which are the dwarfs, almost dust-free systems, and then work our way up. We have about, depending on how you define the dwarfs, mostly we define dwarfs as a low metallicity, low mass galaxy. We have about 20 in LEGUS, and the first three actually have been analyzed and came out fairly recently. And we were able, these are the three color magnitude diagrams corresponding to the three galaxies. What is interesting is how the three star formation histories compare with each other, 449, 1705, and Holberg 2. So you can tell this is more active than this one, which is more active than this one. And to some extent, it shows also in some of the star formation histories, and the wiggles and jumps and hoops are possibly real. Okay? Now, what does it mean? In itself, is simply telling you what is the history of these galaxies. What we're going to do with this, and which we haven't done yet, is compare them with the properties of the star clusters and understand whether the two march along together, or the star clusters are telling us a different story from the stars. And talking about star clusters, how do we identify the star clusters? Okay, and that's the reason why we only have 34 star cluster catalogs. So, first of all, star clusters are easily identifiable up to about 10 times farther distance than individual stars with HST. So, if star clusters really trace star formation the same as good as individual stars, they clearly provide an advantage because you can identify them at much larger distance and still be able to study the properties of star formation. So what we did here was to identify in a way that I will show in a minute, I will explain in detail in a minute, all the possible star clusters in these galaxies. This is 628, the distance of 10 megaparsec, and then have a total of a team of 15 people going through each blob and telling us whether they thought it was a cluster or not. And the next two slides will give you the full details of why we had so many defections in the team. Before LEGUS, there were two, the approach was binary, cluster, non-cluster. How is cluster identification done, at least until today, as far as I know? You run Sextractor or an equivalent software to identify anything that it looks somewhat extended, more extended than your PSF, so than a star. Just to give you a sense from the previous slide, this is the type of plot you're looking at, right? A full width of maximum larger than a few pixels, 3 to 4 pixels. That's what you would call a cluster. And then after that, you have a lot of junk that the Sextractor cannot discriminate. And these are actually the benign ones. You have even ugly junks, like, for instance, spikes from an oversaturated star can be identified as an extended object. So you have to remove those. So you need to have someone who goes through these thousands of sources, candidate clusters, and tell you whether it's a cluster or a non-cluster. And the first thing we realized as a team was that different subgroups had different ideas what a cluster was. So we had one session once in Baltimore where we put everyone in a room and went through a discussion of with a bunch of these cutouts, and discussion of what was supposed to be a cluster, what was not supposed to be a cluster. We had two representatives from two competing teams, Brad Whitmore and Angela Damo. They are on the opposing sides of two theories of cluster evolution. And we asked them, tell us what is a cluster, okay? And so after fighting for 6 months between each other, they finally came to an agreement, and then they trained everybody else to try to recognize a cluster. Of course, when they saw that there was the potential of having a lot of people doing classification, they became extremely sadistic. And they decided that instead of having a cluster non-cluster classification, it would be fun to have multiple classes. The perfectly round ones, the slightly elongated ones, the ones that have multiple peaks, and the ones that are not clusters, so the class 4. Now, if you think that these look all alike, I agree with you. It took me a long time to convince myself that I was looking at 3 different objects rather than the same object with different stretches. So that's why we had to have training sessions, because otherwise this would have been all over the map. But one of the things that we did was that instead of doing what was done until pre-LEGUS, and that the visual inspection was typically done by one person for any given source with no redundancy in identification, we asked that each object be viewed by at least 3, possibly 5 people. That to create redundancy and robustness in the catalogs. So at least we have that if there is a mistake, it's done by 3 people, and if there is a bias, it's all common. Sorry?
They have to all agree?
No, they didn't have to agree. But there was another person, independent of this 3 to 5, who would take all the classifications and we publish the mean and the mode, and the deviation on all the classes. And every time there was more than a factor 2, so if one classified as a 1 and another classified as a 3, if we had too many of these misclassifications, we would call another 3 people to actually break the ties. It took a number of years, and that's why we only have 34 catalogs. But that has given us some of the most robust star cluster catalogs in existence, right? They're public, by the way. We didn't do everything in every single class. So if they have a classification of 1, 2, 3, or some number that is non-zero, they've been looked at. If they have zeros, don't take them, please. Don't use them with science and say these are LEGUS clusters. No, they are not. We didn't look at them. But we have robust classifications, not only that, but we have been able to demonstrate that the class 1, class 2, and class 3 are physically different objects. The class 1 are bound system, and they're symmetric, older in age on average than the ones that are class 2. They can be elongated, they're young, bound, unrelaxed. So they're bound but unrelaxed. And the class 3, the multi-peak are definitely compact associations. We call them compact associations. So there are 3 physically different systems. And there is a paper on that by Angela Damo showing these differences. Post-LEGUS. So after everyone now refuses to look even at any additional yellow blob, we have to come up with a different idea for, first, how we go to fainter objects, because we only classify the brightest ones, and second, how we go for the remaining 29 catalogs. Machine learning is an option. off-the-shelf training, off-the-shelf algorithms that exist even in Python do a decent job for the class 1 and 2. They can recognize roundish blobs. They do a terrible job for the class 3. So for M51, where this is the Zagel line is the coverage by LEGUS, we had the visual classifiers doing these three steps and then telling us forget it. And then we run the rest with machine learning. And the 1 and 2 came out pretty reasonable. The 3 didn't really increase that much. So clearly we need to work if we are going ever to apply machine learning. A lot of people ask us about Galaxy Zoo type of approach, crowdsourcing. The problem with crowdsourcing is that as we needed to train the team members, we will need to do training sessions for the crowdsourcing. And when we did an experiment with the equivalent of Galaxy Zoo, the type of classification that were returned were perfectly random. 25% class 1, 25% class 2, 25% class 3, or 25% class 4. Totally useless. So we can't use crowdsourcing for this type of approach. And the reason is because if you ask people to tell us whether a galaxy is a spiral or non-spiral, it's a lot easier than asking a person in this crowded field, is this blob a cluster or no cluster, right? Makes a huge difference in the level of training that you need to be able to recognize that. So this is what computer scientists call the confusion matrix. What is the classification of the machine learning algorithm versus the classification of the scientist. And they pretty much do well on the class 1 and 2, and the class 3 is horrible, and the class 4 is usually pretty good, but that's all the junk. So it's easy for the machine to tell you what is the junk. So 32% for citizen scientists, the random is 25%. Okay, so however, we accepted the results for one galaxy, M51, and we have the most crowded and the most complete classification of class 1 and class 2 clusters. And that helped because having 3,000 clusters in one galaxy, which is the largest collection of star classes in any given galaxy that in existence, has helped us confirming certain trends that we are looking at. Trend number 1, and actually I put luckily this has appeared because it's important. You separate the sample in spirals and dwarfs. Okay, so the green is the dwarfs, the blue is the spirals. And what you're looking here is the cumulative fraction as a function of mass of the classes that you have, okay, being in mass. This is a power law function of -2 for comparison. And you can definitely tell that the spirals with 4,200 clusters in your sample bend down and have a cutoff. The dwarfs, 16 dwarfs, but the statistics are small, do not show the same bending. Okay? So, first of all, the one result, very robust result, is that spirals, the mass functions of star clusters in spirals follow a scatter function type of trend. Okay? Where there was a debate, there has been a debate until recently whether that was true or was just an artificial effect of small number statistics, whether there were spirals also had a -2 power law type of luminosity function or mass function. And we confirm with 4,200 clusters that that's not the case. There is definitely a cutoff. And the cutoff is around a few times 10 to the 5 solar masses. This is not very different from what Larson determined several years ago. It's just that the statistics are so powerful, the error bar is tiny on this result. The second one is the result on the dwarfs. If confirmed, and the statistics are still poor, the absence of a limit, so a cutoff mass in dwarfs, might have to deal with the fact that the star formation is stochastic and there is low or no shear in the galaxies. So why would you have a cutoff in the spirals? Because shear limits the maximum size of the cloud that you can form and what can collapse. So that would account for the cutoff in the spirals. And would account for the absence of cutoff. The absence of shear would account for the absence of cutoff in dwarfs. Indeed, superstar clusters tend to be fractionally more frequent in dwarfs than they are in spiral galaxies. Another interesting result that we are working on, and actually Angela is preparing a paper on this, is measuring the fraction of clusters that are formed in the galaxy as a function of the star formation rate in the galaxy, in this case of the region that we are sampling with HST. And the prediction from Cruisen in 2012 is this dotted line. I hope you can see it. So the vertical axis is gamma, the ratio of number of clusters, well, of massing clusters over the total star formation rate in mass, and the horizontal axis is the star formation rate density of in the region. And if galaxies or regions within galaxies follow this trend, it means that the star formation is an effect that practically is the hierarchical product, for obvious reasons, of the gas dynamics and gas properties. And now, I always tell Angela that if somebody removes the line, I would just see a scatter plot. But she believes that it's actually a confirmation of the Cruisen model, which could be also true. So I actually challenged her and I told her, okay, we have for all these galaxies Herschel and Spitzer data. We can derive dust masses, okay? And through an educated guess on their metallicity, well, we don't need a guess, we actually look at the measurements of their metallicity, we can derive through a dust-to-gas ratio the total gas content. The reason is because the fiducial model of Cruisen was developed as a function of the surface density of total gas in that region. So I said, let's see if I convert everything to gas, whether it still goes there, goes through the line. So this is the plot. So this is the model, the original model by Cruisen, and this is where the LEGUS galaxies are, okay? As a function of the surface density of gas. There is a huge scatter. It follows the line, but again, you remove the line, it's a scatter plot. The problem is that the dynamical range that we cover is small. And the spread is actually understandable if you remember that this model depends on omega, the angular velocity, the Turner parameter, and there was another parameter, the surface density of the gas itself. Okay, that's already in here. So the angular velocity and the Turner parameter also affect where the location and the spread on the relation. So to some extent, this is not confirming, not dismissing that model. Clearly, if we can fill in this region here and this region here, we'll be able to confirm whether the model is acceptable or not. But clearly, it's also telling you that, again, this is a model that is based on the turbulence, survival of the star clusters in a turbulent medium that is within a galaxy and is environment dependent. Now, one other experiment that you can make when you have so many clusters with so many ages and masses is to ask yourself the question. If it's really true that there is a hierarchy, then you have a positive two-point correlation function. What is a two-point correlation function? Is you measure the distance between two clusters and check whether if they're closer or not than if they were randomly distributed. Okay? So you take all your distribution of pairs and then create a random catalog and measure the distribution of pairs in a random catalog and take the ratio of the two. That's what a two-point correlation function is, very briefly. And you can definitely tell that the two-point correlation function, which in the case of a perfectly random distribution would be along the zero line because it's a log scale, okay? So this is the ratio of what you observe in terms of pairs divided by the pairs that you get from a random catalog. And you can definitely tell that they are more correlated than a random distribution. Not only that, but the younger clusters are far more strongly correlated than the older clusters. Okay? So this is telling you that not only they are more correlated, they also dissolve or disperse over what time scale? About 40 million years. Now, the fact that the clusters are correlated is not new, but the time scale is. We didn't know it was only 40 million years. Most of the theories were talking about either very much shorter or much longer. How the clusters migrate, because that's the next question you want to ask, right? There is a prediction that if turbulence dominates the medium, the age difference between two clusters increases with their distance. Okay? They migrate. With what kind of power? 0.5. If they were just a standard migration through a random walk, the power would be 2. Secular migration, the power would be 1. Turbulence driven, the power is 0.5. This is not my theory, okay? Ask Bruce if you want, but it's practically the Larson law applied to star clusters. So delta tau is the maximum duration of the star formation within the largest coherent region possible in the galaxy, but also the age difference between any given pair. You measure the age difference between any given pair in any galaxy, and this is these are small cutouts of a larger plot, as a function of their separation. And you measure the slope, and it's close to 0.5. It actually has some variations, it goes from 0.3 to 0.6. But if you only select a cluster that are younger than 100 million years, it's much closer to 0.5. And this is in 8 galaxies. Not only that, but we observe a breakpoint in which the clusters become totally random. Okay? The size of that region is between 0.2 and 1 kiloparsec in these galaxies. The velocity, the maximum age at which this happened, goes from about 30 to 90 million years. So they look like they're all over the map. What is not all over the map is the ratio of those two numbers. The maximum velocity at the edge of your coherent cell, okay, divided by the shear is a constant. Meaning that the largest coherent cell that you can have of star formation is limited by the shear in the galaxy. One more application, and then I'll let you survive and go. What time is it? Okay, I still have quite some time. So I can continue to torture you. Okay. These galaxies, again, are very nearby, and they've been observed in many, many bands, including CO. Okay? For now, we only have 2 maps. This M51, the galaxy for which we have the machine learning cluster catalogs, they've been observed by Eva Schinner's POST project with the Pâté de Bureau. And the 7793, we got ALMA data fairly recently. And so we overlapped the maps of star clusters and molecular clouds. I mean, it's the easiest thing that you can do. One of the questions that you can ask is separately, okay, if the star clusters are correlated, and the younger star clusters are more correlated than the older star clusters, the molecular clouds should follow the young star clusters. If you take all the molecular clouds, they don't. They're much flatter. But if you only select the giant molecular, those are the lines. So all the molecular clouds are the black continuous line. The continuous line are the giant molecular clouds. The dashed line are the star clusters. So if you take all molecular clouds, the black line, continuous line, they are kind of flat. They don't follow the young star clusters, which are this dotted dash line or the black line, the dotted and black and magenta line. But if you select the GMC that are more massive than a certain limit, so you take your star clusters, we have a mass limit of giving them an age and a mass. And the reason is because we can't give an age and a reliable age to something that is below about 3,000 solar masses. Why? Because we are become a prey of stochastic sampling on the stellar initial mass function, and the uncertainties become enormous. So we gave a limit to of about 3,000 solar masses. Now, if you assume an efficiency of star formation of a few percent, that means that the parental cloud of a 3,000 solar mass cluster must be 10 to the 5 solar masses or larger. So you then reproduce the two-point correlation function, not for all the GMCs, but only for those that are more massive than 10 to the 5 solar masses. And that's the cyan line here. Okay? And that's pretty much follows the two-point correlation function of the young massive star clusters. So actually, this is the limit we put was 1,000, not 3,000. Okay, so that's no mystery. Massive giant molecular clouds followed are as clustered as the young star clusters. The interesting point is that all molecular clouds are not clustered. Okay, they are very little clustering, so they're randomly distributed across the galaxy, and that's for both M51 and 7793. M51 is a grand design spiral. 7793 is a flocculent spiral, SD. The other experiment that you can make is, okay, I know where all the molecular clouds are, and they have a footprint, because the catalogs publish both the position and the size. And then I can count how many clusters are on top of the footprint, okay? How many are 2 times away from the footprint, 3 times, and so on and so forth. And measure the median age of those populations. So you go from, for M51, for instance, but the story is similar for 7793, you measure the median age for the ones that are within one radius of a giant molecular cloud, 2 radii, 3 radii, and more than 3 radii. And practically you go from a median age of 4 mega years in M51 to 40 million years at the largest distance. This is telling you very clearly, and not surprisingly, that the younger clusters are smack on top of a giant molecular cloud. The oldest ones are farther away. Okay? What is the time it takes for a typical star cluster to move away from a giant molecular cloud? About 35 million years. Okay? It's 40 million years. It takes a much shorter time to 7793, and we have been puzzling for a long time on the reason why 7793 in 7793 it only takes only 7 million years, right? Not 40. Why is that? And not only that, but these time scales for 7793 are much shorter than the ones that have been measured in the SMC, the LMC, and M33. So it's not like, what is funny about this galaxy? This galaxy doesn't have, 7793 only has young star clusters. Doesn't have a lot of star clusters, old star clusters. Mostly are young, younger than 10. While M51 is a standard galaxy has been producing star clusters for a long period of time. They cover the entire age range that we can probe. So, Kati, the student who has worked, Kati Grasha, the student who has produced these papers, said, okay, let's divide the age that we measure at each distance, so distance to the GMC in, so 1, 2, 3, more than 3, let's divide it by the median age of the population we are sampling. And both 7793 and 5194 overlap, okay? Which is telling you that the time it takes for a star cluster to separate from its parental cloud is about half of the median age of the cluster population. The median age of the surviving cluster population, not just the cluster population, the surviving one. So it's possible that clusters in 7793 do not survive for a long period of time, and they dissort before they can actually be measured at old ages. Or they just started to form recently, although there is no evidence that they only started to form recently. Conclusions. Star clusters track star formation in galaxies, and that's an advantage because we can give ages and masses, and are allowing us to link in the local and the global star formation. The UV is critical to give a proper age to the star clusters. There have been various attempts, including using H-alpha. H-alpha is good to separate something that is younger than 5 million years from something that is older than 5 million years. But if you want to age data between 5 million years and 20 million years, you need UV. Otherwise, you collude all of these classes into one age bin, because H alpha is no longer good at that point. Star formation is hierarchically clustered, no surprise there, it was already known, but we have a spatial scale now. It's about 0.2 to 1 kiloparsec. And although there is the possibility that the limiting factor is the scale height of the galaxy, so that we haven't excluded that because we can't really measure the scale height of these galaxies, we can definitely tell that shear has something to do with it, because the velocity at the edge of the transition point of the largest coherent cell divided by the shear is a constant across very different galaxies. And the clustering is consistent with star formation driven by turbulence. That's the delta H versus separation and the cutoff that we observe. Massive GMCs closely mirror in clustering that of their children clusters. So massive star clusters and massive GMCs have similar two-point correlation functions, but GMCs are in general far less clustered than star clusters, unless we are comparing GMCs with old star clusters, in which case they are both uncorrelated. But this was slightly surprising. It took us a while to understand what it really meant. The randomization timescales for the structures are of order 30 to 90 million years, so it's not a huge amount of time. It takes very little time for any coherent structural star formation, unless it's bound, to actually randomize completely within the galaxy. And that's why it can be very confusing, because sometimes you see UV bright populations that are about 100 million years, which are almost completely filling up a galaxy, because it takes very little time for them to randomize. And the star clusters separate or evaporate from the GMC over time scales that are about half the median age of the surviving cluster population. That's the last slide I showed. So the future. We hope to extend these studies by using machine learning to identify more clusters robustly. Hopefully that will happen in the future, in the near future, and search for second-order effects on these results, and also try to trace the younger stars, the younger phases of star formation through infrared from HST, JWST, and ALMA. Thank you very much.
We have plenty of time for questions.
I'm a bit confused by your star cluster separation. It seems to me we're going around the galactic boundary here, the star cluster moving away.
Yes.
If they actually do that, why would they do it together instead of dispersing?
No, they disperse. The star cluster. So there are two mechanisms that we can one which we can't measure, the other which we can measure. One is the secular separation of the cluster from the cloud. Okay, and that's the one that in M51 occurs over 40 million years. There is a component that we cannot measure, which is how many clusters actually get destroyed before we can measure them. And that is something that we haven't been able to measure, because what we need is to know the star formation history from the stars first, to know how many wiggles, bumps, and hoops the star formation has had over the past, say, 100 million years, and then we can count the frequency of clusters in each pin. So, but we haven't done that yet.
Some of them do actually move together.
Oh yeah. The clusters that we measure, class 1 and class 2, are bound, so they stay together even after they move away. Well, at least over the time scale we measure, they stay together.
Yeah, a comment about this second point in your conclusions. You can check this statement about the scale height, because it's pretty easy to measure. You need to recover the vertical component of the velocity dispersion disk. So you either measure directly the velocity dispersion in the disk if the galaxies face on, or you use the asymmetric drift and the equations of the disk stability to basically estimate the z component. And z component gives you the thickness of the thin disk, and thin disk thickness is what you can assign as the scale height.
Okay. We haven't done the experiment.
But you need data.
Yeah, no, I understand. We need you need additional data, and we haven't done the measurement yet. Mostly for lack of time. These are off the press, and these were published very recently.
So if these clusters stay together at least for 90 mega years, because that's what you see, that means there are no supernovae going in.
So, or if they're going off, they're not destroying the
Then
cluster.
destroy the cluster. Have you looked into that? Because that could give either a top mass for the
So
mass function, or
we can't separate the age from the IMF, and that means that we are assuming an IMF. We see plenty of UV light, which makes us suspect that there are massive stars, but we don't know for a fact. Now we have one measurement in NGC 5253, which is a dwarf, which we are able to get everything out of it, because HST not only had covered our bands, but also there were additional bands, including narrow band, and these are whopping in H alpha. Actually, no, we know that there are at least several massive stars, because they are ionizing. So there are ionizing stars. So they are more massive than 20 solar masses. Whether they reach all the 120 upper limit, we don't know. But in NGC 5253, we were able to establish that not only had to be 120, possibly even as much as 200, because we see potential signature of super massive stars, very massive stars, the BMSs.
So, point 4, the GMCs being less clustered than star clusters. Does that just mean that there's more than one star cluster per GMC?
We looked into that. On average, there is typically one young star cluster per GMC, but not all GMCs have star clusters. They could be forming stars. So there are two options here. They are forming stars in a way that we do not pick up as a star cluster. Okay, maybe they are much lower density, and our automatic system mechanism of Sextrator cannot pick them up, or they are very low mass and we don't pick them up. The third possibility, so there are three possibilities actually. And the third one is that they are still dust enshrouded. But then dust enshrouded.
Oh, dust enshrouded.
And that's why we have an infrared program on Hubble to actually check that.
Yeah. Right near the beginning, you had the statement that 8% of the star formation was clustered.
Bound clusters, yes.
Was in clusters.
Bound clusters.
Ah, maybe that's it. Then what's the rest of the 92% is what I was wondering.
Field stars.
And so you're only looking at 8% of the star formation.
So that's an interesting point, because that point needs to be reconciled with this result here, right? So according to this result, you go from about 4% to 70%. That is just a blunt average.
Okay.
Can be pretty high, at least in the fields that we target. Okay, so these are not, in many cases, these are not entire galaxies. These are fields within the galaxies.
Second question related to this. So does this 8% account for this infant mortality of star clusters?
Yes.
Okay, and then can this association between GMCs and star clusters be the answer to the discussion we had yesterday on the Schmidt-Kennicat relation in like normal quiescently star-forming galaxies versus starbursts?
In what sense?
In the sense that when you have GMCs which are not forming star clusters, the conditions are not the same, and they have something to do with the H1 distribution, because they're sort of separated. You see that you've shown this correlation function that tells you that GMCs are randomly distributed in the galactic disk, basically like the H1 gas. And it's not like those very massive clusters that you see, which are correlated.
Yes, so first of all...
and in star clusters, they're all in the same place, basically.
Yes, but in this case, these are all normal star-forming galaxies. There's not a single starburst in this sample.
Okay.
Okay, so even the most active one is M51. It doesn't qualify as a starburst by any stretch of the imagination. So I'm not sure if I understand exactly what you're saying, but we don't have starbursts, so we cannot check it. At least not with this type of approach.
Okay.
Now, there is a study of the antennae that puts the data points. Oh, I think these are these ones here. Let me see. I think these 3 data points could be either the antenna or at the center of M83, which is a starburst central region. They tend to have more higher fraction of star formation converted into star clusters directly. In clusters, yes.
Okay.
If the maximum mass of a cluster depends on shear, then wouldn't you expect more massive clusters always to be in the outer parts of galaxies?
So, sorry, maybe I misspoke. What I meant is the largest cell of coherent star formation. So so you have the hierarchical star formation, of which the star clusters only identify the peaks, right?
Okay.
But if you look at how stars distribute, UV star bright stars distribute, they come into increasing hierarchy, lower density, broader regions. What is the largest scale that you can do? And apparently shear seems to be the limiting factor.
So that should, but still, that number should be bigger in the outer regions than in the inner regions.
We cannot check that because we don't have enough statistics.
Ah, okay.
So, but that's a good point. The problem is in the galaxy where we go out enough, the star cluster population is so slim, we can't really tell.
Yes.
So we have, we spent. Let me see if I can get there. Okay, yeah. So for M101, we had 1, 2, 3, 4, and 5 fields. Okay, these 2 fields are cluster rich. This is okay. These 2 have virtually very few clusters. You can't do anything with them. Those fields, which tend to be very dust-free, because this galaxy has a steep metallicity gradient, will be great for doing star formation histories, but not so much for doing anything with the star cluster population, unfortunately.
Could you remind me again, how did you determine the ages of the clusters? Was it just from the UV, or did you have other?
No, it was an SED fitting of through SED fitting.
And so you assumed an IMF, and you had a census.
Yeah, the IMF we have to assume, unfortunately. Michele Fumagalli with Greg Ashworth, which is a former student of his, they tried to use a Bayesian approach to see if they could separate all these parameters. Mass is not a problem, but extinction, age, and IMF. And their posterior probabilities practically are this beautiful flat distribution that occupy the entire parameter space. So you can't really discriminate the IMF from the age, which we already knew, but it was good to actually have it published somewhere.
And as you know very well, extinction is a big issue here. So how did you measure the extinction?
The fitting that tells us
the fitting.
Because so if you use the U-minus UV, that is an extinction leverage arm. U-B is a strong H arm, and the V-I gives you the intermediate arm between the two to make the degeneracies. And that's why we selected those 5 filters. So it took us quite a while to settle on those 5 filters, because we wanted to have the maximum signal to try to break these 2 degeneracies, age and extinction. IMF we can't discriminate.
Any more questions? Okay, let's thank Daniela.
Relating to your question, the odd thing, one odd thing that's